Hello everyone, in this video we will cover the section 1.2. In this section we will see solutions of some ordinary differential equations. Especially we will we will deal with separable ordinary differential equations. This is a method called separation of variables, namely to find the solution of separable ordinary differential equations. We will use a method called separation of variables. In this method we gather same variable into one side of the equation, and then we use integral formulas for finding the solution. In the preceding section, we have a differential equation for amount of drug in a bloodstream. If you remember, this is given by the derivative of amount of the drug with respect to time is equal to 500 minus 0.4 times a. So how can we find the solution of this differential equation? This is first order differential equation. We will see in the next section the definition of the order of the differential equation. Since we have the first derivative of the dependent variable, so we say it is a first order differential ordinary differential equation. According to the separation of variables, we will gather the same variable into one side of the equation. Namely, you see we have the variable a and we have the variable t actually. So to gather the variable a into one side of the equation, so we write dA over 500 minus 0.4 times a dA, which is differential of a, is equal to dt. Okay, and then we will use integral formulas for finding the solution, because we have the same variable on the left side of the equation, which is the variable a, and on the right side of the equation we have the variable t. Let's continue here. dA over 500 minus 0.4 a is equal to dt. So from here, according to the integral formula for this case, if you remember, the general statement is 1 over ax plus b, the integral of 1 over ax plus b dx is equal to ln ax plus b over a, if you remember. So from here, using this integral formula, so we obtain ln 500 minus 0.4 a is equal to the integral of the right side. Actually, we consider this is 1 times dt. So the integral of the number 1 is, t plus c, which is the integral constant. Okay, since we have indefinite integral. So from here we will find the variable a in terms of the independent variable t, which represents the time, if you remember from the preceding lesson. So to get directly this term, so we take the exponential of the equation, because we know exponential to the power ln y is equal to y, if you remember. Therefore, the left side becomes 500 minus 0.4 times a is equal to e to the power before this, according to the formula, we should write also over a, namely the coefficient of the variable x. Therefore, we write over the coefficient of the variable a is minus 0.4. Therefore, writing this number to the right side of the equation, we will see, we can write the left side. Let's write again ln 500 minus 0.4a is equal to minus 0.4 t. So minus 0.4 times c becomes another constant. Let's say for this c1. Okay, c1. So from here now we can apply this formula, this rule, to find the independent variable a in terms of the independent variable t. So from here we have 500 minus 0.4a is equal to e to the power minus 0.4 t plus e to the power times e to the power c1 will be another constant. So for this, let's say c2. And then we have 500 minus c2 e to the power minus 0.4 t is equal to 0.4a. And then a becomes 1250 minus c2 over 0.4 is another constant. Let's say for this c3, e to the power minus 0.4 t is equal to a. So we found the dependent variable in terms of the independent variable. Now we know the definition of the function written here by solving the differential equation. Explicitly we can see now the amount of the drug in bloodstream at any time, just writing a value for the time, and then we can find the amount of the drug clearly by using this function after solving the differential equation by using the method called separation of variables. Okay, but here still we have unknown, which is the constant c3. So how can we find the constant c3? So it can be found if we have an initial condition for the dependent variable. If we say the initial condition, namely the initial value, namely at t is equal to 0, what is the amount of the drug in the bloodstream? What is the amount of the drug at the beginning of the process? So it will be 0. Therefore, a of 0 is equal to 0. Using this initial value, we can find also the constant c3. Writing 0 for t, so the right side will be 0 from the initial condition. So we have 1250. Writing 0 for t, we get e to the power 0, which is equal to 1 minus c3. From here, c3 becomes 1250. Okay, writing this, now we have exactly the amount of the drug at any time. Okay, so you see, first we model the problem mathematically by using the differential equation, and we solve this differential equation, and we obtain the function which states the amount of the drug in the bloodstream at any time. And then using the initial value of the problem, we solve exactly the problem. Now we can find the amount of the drug for any time by using this function. Okay, this is the exact solution of the differential equation, which is the model of the problem. So you can see also from here the additional condition a of 0 is equal to 0, initial value of the problem in the example above, is called an initial condition that we say, and the equation with initial condition forms an initial value problem. If you have initial condition for any differential equation, so it is called an initial value problem. Okay. Another example, according to Newton's law of cooling, the temperature U of T of an object satisfies the differential equation where bigger T is the constant ambient temperature and K is a positive constant. Suppose that the initial temperature of the object is U of 0. So we have initial value for the differential equation, therefore it is an initial value problem. The temperature is stated by the function of T, which is denoted by U of T, okay, of the object, and it satisfies the differential equation, namely the temperature is modeled by the differential equation here, and we know its initial value. So now by finding the solution of this differential equation directly, we can find the temperature, which is a function of T. Okay. By using the same method, let's continue here. Let's write first the differential equation, du over dt, du over dt is equal to minus k times u minus t minus k times u minus capital T. Using the same idea, the dependent variable is u, the independent variable is t. So we have two quantities in the production here, in the product here. Therefore we write, to get the same variable in one side of the equation, therefore we write du over u minus t is equal to minus k times dt. Using the same integral formula written here, the variable is u and its coefficient is 1, therefore taking the integral of both sides of the equality, we have ln absolute value u minus capital T is equal to, we have a constant which is minus k. What is the integral of constant? You know, minus k times t plus the integral constant for both of them. Using the same idea, namely we take the exponential of both sides of the equation, therefore we have from the left hand side u minus t, and the right hand side becomes e to the power minus little k times t times e to the power c, which is another constant. Therefore we assign another statement for the new constant c1, and from here our aim is to find the variable u. Therefore we write u is equal to bigger T plus e to the power minus k times t times c1. Okay, this is the solution of the differential equation, but still we have an unknown, which is the constant c1. It is found by using the initial condition u of 0 is u0. Therefore, and we know when we write 0 for the independent variable, we obtain u0. Actually it is a function of t, u of t. Writing 0, the left side becomes u0, the right side is bigger T plus When we write 0 for t, we get e to the power 0, which is equal to 1. Therefore, the last term becomes c1. So from here, c1 is equal to u0 minus bigger t. Writing this into the solution, we obtain exactly the solution of the differential equation, which states the temperature of the object. So we have t plus this constant c1, which is u0 minus bigger t times e to the power minus k times the independent variable. Okay, this is the solution of the differential equation given in the example. Also, you can see here, this represents the temperature of the object at any time after solving the differential equation. Therefore, you can increase the number of examples by understanding where. For example, let's find this one. Let's find the solution of this differential equation. Similarly, instead of y prime, we use the Leibniz notation to see clearly the variables. Dy over dx cosine y is equal to cosine x. Dependent variable is y, independent variable is x. So to get the same variable in the left hand side or right hand side of the equation, let's write dx to the right hand side. So we obtain cosine y dy, and the right hand side becomes cosine x dx. Okay, the integral of both sides of the equation becomes, what is the integral of cosine y with respect to y? It is equal to sine y, and the right side also sine x, plus the integral constant. And from here, the variable y is equal to, by using the inverse trigonometric function sine, which is written as arcsine sine x plus c. And we don't have any initial condition for the differential equation. Therefore, just we know the general solution with the constant c, which is written as y is equal to arcsine sine x plus c. This is the solution of the given differential equation. Similarly, you can find the solution of the second one, which is written here. This is your homework. Also, you have another homework. Please solve these questions, and if you have any question about that, please inform me. Thank you for listening and watching.